Thank you all for joining us and welcome to the next installment of our Sustainable Energy Seminar Series. If this is your first time, my name is Scott Williams. I'm the Research and Education Coordinator at the Wisconsin Energy Institute. And the Sustainable Energy Seminar is held through the Wisconsin Energy Institute every other week during the fall and the spring semesters to highlight the many cutting-edge energy research activities from across UW-Madison. And it's our way of showcasing how different disciplines understand energy challenges and develop solutions. So throughout this series, we'll hear from experts in science and engineering, as well as social sciences and humanities, to learn about the many ways in which they view these sustainable energy challenges and solutions. This seminar is open to the public, but it is also a one-credit course for students in the undergraduate certificate in engineering for energy sustainability, as well as the master's in sustainable systems engineering. We're offering this seminar online for the fall semester, and you can sign up for any of the dates for this seminar series in the same registration link that you used for today's seminar. You might have noticed live captioning is available for those who would like to use that feature, and you can click on the live transcript button to toggle that feature on and off. If you'd like to ask questions of our guest speaker, you can use the Q&A box. I'll be monitoring that throughout the talk, and Professor Hampton has said he's welcome to being interrupted to answer any questions that are related to his presentation. So with that, I'll introduce today's speaker. Dr. Jesse Hampton is an assistant professor of civil and environmental engineering. He leads the geomechanics and damage group at UW-Madison. And this group studies both fundamental and applied topics in geomechanics, petrophysics, and geophysics. And the main objectives of this research are to address some of the fundamental issues of geological engineering as they apply to geothermal, oil and gas, energy, waste and carbon dioxide storage, underground construction, tunneling, and planetary rock and soil mechanics. So today he'll be talking about the potential for enhanced geothermal systems to provide a clean and reliable source of electricity, as well as some advances and challenges for this technology. So welcome.
Well, thank you. Thanks for the introduction. And like Scott said, I'm an assistant professor here at UW. I started in just a couple of years ago, and we're going to talk about a few things. One of which is kind of a background of enhanced geothermal systems in general. And please do go ahead and just interrupt me whenever you have a question, and we'll go from there. So for the talk today, I'm going to give a little bit of a background of just myself and who I am, and to try to give maybe some credibility to what I'm trying to say. And then we're going to go into just what is enhanced geothermal systems at a super high level scale. So 30,000, 40,000 foot scale. We're not going to get into really fine detail on a lot of the topics, but we will dive into a couple of them a little bit. So we'll talk about what is enhanced geothermal systems. And then we'll also talk about some of the current challenges in EGS, and mainly have that framed through the context of, where is the research ongoing right now? So for instance, what is the Department of Energy funding? What areas do the Geothermal Technology Office think that are high priority areas? And you can see that usually just by monitoring what funding announcements are available. So we'll look at some of those and see kind of what the projects that they're currently thinking about. And then we're going to move into a little bit of my particular background, which is not, it has been on EGS projects even in graduate school, but most of my background is in something called nondestructive evaluation. So we're going to talk a little bit about that and introduce that, and we're going to use these non-destructive evaluation tools to see what we can provide and actually help with some of these challenges for EGS. A couple of them that we'll try to focus on are, acoustic emissions and possibly fiber optic sensing here. There are many non-destructive evaluation tools, and like we're going to talk about in a few minutes, there are many challenges that I'm not going to list with enhanced geothermal systems. It's just a very broad, open, multidisciplinary field. There's no way I'd be able to, well, one, there's no way I'd have the expertise to cover all of the challenges because they're multidisciplinary. And two is that it's only 45 minutes, you wouldn't be able to cover everything. So then we're going to go into just a little bit of background of what my current team is working on here at UW, and we'll try to frame that with some of the challenges in EGS. So as a background for me, I did my bachelor's at Old Dominion University, and it was mostly water resources engineering and coastal engineering, and trying to understand how erosion was happening on the eastern side of Virginia. And then I moved into Colorado School of Mines, where the focus was my graduate research projects were actually EGS projects that were funded by the US Department of Energy. And we'll talk about some of the work that came out of that in a little while. I then spent about 7 years in the oil and gas industry, doing research, geomechanics research, trying to understand rock behavior and how rocks behave when they're damaged. But some of the main themes of my research are trying to understand damage evaluation. So this speaks to the point of trying to understand, use non-destructive techniques to be able to find out if there's flaws or microcracks or nonlinear behavior within structures, and then trying to say something about the elastic properties as well as the damage evolution as well. So I use lots of different geophysical methods or NDE methods to do this. I'm also been traditionally very interested in understanding how these problems interact across scales. And so this is going to be kind of a continuous theme throughout the presentation, and as well as my research in general, is how do physical properties that we measure at one scale, how do they relate to physical properties at another scale? Because when we look at EGS in the field, we're looking at things that are on the multiple kilometer scale. But there's physical phenomena that are actually manifesting themselves in observable responses that are occurring because of very fine scale things. So we have to integrate all of these scales together to be able to understand what's going on. And then one of the last pieces is so we do that with lots of laboratory techniques, at least in my group, in my background. I'm an experimentalist by training, and so we try to recreate a lot of this environment in the laboratory. And so we'll possibly create fracture systems in the lab under heat and stress conditions and try to understand what's going on while things are fracturing. And then we try to represent those and understand what the fracture systems are doing in terms of how they're interacting and what's going on in the field downhole. So for my teaching background here at UW, I teach a couple of geological engineering courses. One is seepage and slopes. It's all about slope stability and saturated and unsaturated ground. And I also teach soil mechanics every year as well. So one of the courses that I do teach that I did start when I arrived here is called Nondestructive Evaluation. And I teach that every 2 years in the fall, so I'll be teaching it next fall. And that particular class is really interesting because we're diving into some of these different techniques when we are trying to look at flaws within civil engineering structures or mechanical structures or geological structures as well. So I do that with the thought of trying to put it in through the context of geothermal resources, as well as using remote sensing techniques and describing remote sensing techniques and trying to understand the data that comes from some of these sensing techniques. And we're going to talk about the link between the data and data science work that's done in geological engineering and how that connects to the remote sensing and geothermal aspects as well. Because when we get to it later, when we talk about fiber optic sensing, some of the technological advances have come a really long way in terms of being able to create sensing techniques. But our ability to be able to mine the data that we get from these large data sets, it has not gotten to the point yet where it's similar to the remote sensing techniques. So there's a lot of work still to be done in those areas. So what is EGS? So there's I put a link in the top. There's a really interesting, and in my opinion, a very good Vox article on what is EGS. It talks about what is geothermal energy, and how do you get it. And then one of the subsections in the article, it talks about EGS as well. And it does a pretty good job of that. So, when the slides are shared afterwards, please go ahead and take a look at that article if you're just not familiar with it as well. And but EGS effectively, taking a step back, traditional geothermal systems or hydrothermal systems are where we access relatively hot or surface expressions or near surface expressions of hot locations. Think, Iceland or California or some places in New Zealand where you actually have hot rock and magma reaching close to the surface. And some of those areas have groundwater that's heated by these near surface expressions of heat. So you can mine the heat by pulling water out or putting water circulation in and pulling out. But what's really, really interesting is in enhanced geothermal systems is where you drill down to an area that's actually just considered hot, dry rock. So you can go in basement crystalline rock, and the heat resource that's there is not necessarily from, depending on where you are, not necessarily from magma, but it's more from things like radioactive decay of the elements. And it's hot, dry rock. There's not really water there, but you can drill down into the well, into the reservoir here with a well. You can create fracture systems by pushing fluid into the reservoir and creating these hydraulic fractures. And you can also access some of the existing fracture networks that are already there. And then you can drill other wells to meet some of these fracture systems. And what's really interesting about this is you can then create this not necessarily closed loop system, but near closed loop system where you can put in cool water and you can extract steam and hot and boiling water from the other wells, which is a really, really interesting thing, because then you could do this in a lot of locations. You're not restricted to just, say, things in Iceland or California where you actually have surface heat expressions. You can drill down to hot, dry rock virtually anywhere. And it has a lot of geological engineering concepts and problems associated with this type of work. And so we have to worry about how to drill a well that goes many times several kilometers deep, and then have to design how to fracture or create or engineer these networks of fractures, because you want to be able to put cool water in and have it go through the fractures at a reasonable pace to pick up heat from the rock itself, and be able to have enough of a throughput to be able to get steam and production of water on the other wells. And you always have to look at the life cycle of this process as well. As we're injecting fluids in, we're extracting heat from the rock, but if we want to make sure that it does it in a renewable sense, then we want to make sure that when we're injecting fluid in, we're not oversaturating a certain area and cooling it off, because it'll eventually come back in temperature, but it might take some time. So you want to engineer the system such that the fracture systems are efficiently designed, where you can still extract heat continuously. So this is one of the many technologies that the U.S. Department of Energy thinks is going to supplant some of the fossil fuel areas as well. So, and what's really interesting about this technique is it gives a lot of the technologies that have been developed in oil and gas extraction a safe and renewable area for them to go. So a lot of the same concepts of drilling these deep wells and creating these fracture systems can be applied and used in a more renewable sense, which is really, really exciting. Something came up. oh no, Scott just posted the Vox article in the chat window if you haven't already seen it. So we just talked about this. There's lots of different things that are ongoing and from a geological engineering perspective in enhanced geothermal systems. It's a very large project. Each of these types of projects are very large, where you have to be concerned with quite a few things that are going on within the subsurface, and you're also not able to actually see what's going on in person. It's not like when we design civil engineering structures where we can specifically design the type of concrete in a certain beam, or we particularly design use a particular steel for a steel bridge. When working with the subsurface, the ground and the geology of the environment is oftentimes unknown. So we have understanding of what's going on within the subsurface somewhat, but we're not going to be able to really image and know what's going on exactly, 10 kilometers beneath the Earth's surface very well. So we have to do a lot of innovative imaging and design work to be able to at least get a handle on what's going on. So it's an interesting area of work, because oftentimes you know less about what's going on 10 kilometers beneath the Earth's surface than you do at, say, creating a small structure on Mars that an inhabitant can be for a certain amount of time. So you can actually validate what's going on when you're next to it and image it with multiple different things, but when it's 10 kilometers downhole, it's not really feasible. So some of the challenges associated with that being a geologic environment brings is we don't really understand, or there aren't a lot of good ways to understand or physically measure the state of stress within the Earth. So there's a lot of ways to calculate things, and there's several different ways to create small fractures to try to understand what the stress is doing. But it's really hard. It's an active area of research to understand what the state of stress is within the subsurface. This is one of the things that controls how these rocks behave. It's if you think about the two most important things with understanding the fracture system and understanding the subsurface environment are, one, the stress of that environment, and then two, the physical properties of the materials. And oftentimes the stress is even more of a controlling parameter than even the physical properties. So understanding the rock properties, that's the second piece. That's one of the major challenges, is because if this is all going on 10 kilometers beneath the Earth's surface, then we don't really have a great way, other than taking core material from wellbores, of pulling the rock out and actually measuring some of its elastic properties and failure properties. So we have to use a lot of inferences from other measurement techniques, and very rarely do you actually get a substantial amount of core material because it's so expensive. So we have to design these things in such a way that we have to be ready for understanding the range of physical properties of these different environments. So one of the other topics that is trying to understand how the fluid is moving through these fracture systems. So if we create this fracture system, we don't really know also where all the fractures, how they're connected, and what the most efficient fluid pathways are at a given time. We can understand what, when we put in fluid in one area, we can measure the pressure response in another area, and we can try to understand what's going on between it. But we still, again, don't have a perfect image of these fracture systems that are 10 kilometers below the surface. And then one of the last pieces is an area that I work in as well, is trying to understand induced seismicity. So anytime we start injecting or producing water from subsurface, we want to understand what the potential is for induced seismicity, as well as some of the characteristics. So typically in geothermal, it's a lot less susceptible to problematic, I would say, induced seismicity than, say, wastewater injection from oil and gas, because in those environments you're putting in millions and millions and millions of gallons of fluid, and it's pressurizing the subsurface. So we don't really know, have a good handle on what's going on there, as much as in an HES system you're not putting in as much and leaving it there. So it's typically a little bit less susceptible than things like wastewater injection. You can see that from some of the ongoing induced seismicity that's from Oklahoma. So we see some of these challenges, and we had this large problem of trying to transition away from petroleum resources, and this is kind of one of the very interesting and really productive pathways to be able to get there. So we try to look at what the next thought here is to look at what funding EGS has available to it for research. So that was going to tell you a little bit about, well, what are the problems that some of the biggest experts in the field think is going on for EGS? Something's going weird with my computer. Hold on. So one recent project from 2019, the DOE had funding available for understanding the state of stress, like we just mentioned, as well as understanding lost circulation. So the first one we just talked about is trying to understand the stress in 3 directions, so X, Y, and Z, in the subsurface environment. So UW-Madison actually was awarded a large grant in this area called the Whole Scale Project. I'm one of the many members of this team as a co-investigator. And this particular project is trying to understand the state of stress within a geothermal reservoir at multiple time scales as well as multiple length scales. So trying to understand it from the wellbore diameter size, so on the order of a few centimeters to meters, all the way to the geothermal field scale size on the order of a couple of kilometers. So this takes in lots of information. So trying to understand the state of stress from just the overburden material that's there, as well as any tectonic stresses that could be there as well. And then adding in kind of the stresses induced from fracturing activities and then production activities and then plant shutdowns and things like that. So we try to understand, this is an ongoing project, and it's a very interesting project looking at state of stress at the San Medio geothermal field. So the other part of this, lost circulation, there was another team that was funded for lost circulation. And what that means is we don't typically have a perfectly closed system because we're in this deep earth environment. So you say you have an injection wellbore here, we're looking at a top view. And we have a production wellbore here. We'll call this injection and call this production. So you inject into this field and the fluid moves through the system from one wellbore to the other through these fractures that could be between the 2 wellbores. But 100% of the fluid that you pump in doesn't reach usually the other wellbore on the other side. It could range in percentages from wildly different numbers depending on the geothermal field. So that lost amount of water within these fracture systems is one of the issues that we want to reduce, this lost circulation. So you're leaving water in fractures in the deep subsurface. And so they're funding an area to try to reduce this lost circulation within a geothermal reservoir. So one of the next ones, so the Department of Energy has also created what's an interesting area called the Forge Lab, which is an underground laboratory. So it's effectively a DOE-funded geothermal field where at the Utah Forge site, there's a large area of hot, dry rock between 2 8,000 feet depth boreholes, and ongoing research and activity is in that region just so that we can have active projects going on to test these different things before to move them down the technical readiness level to be able to get them to a point where companies can then take them and start implementing them into field situations. So this is kind of the field application stage of some research concepts. And the DOE regularly releases different solicitations for funding. And you could see we're actually, as the United States is putting quite a bit of funding into this. And hopefully it keeps up, because I think that it will be one of the biggest areas that could actually have a substantial growth in the next 20 years. I think the DOE had mentioned that within the next, I forgot the year timeline, it was like 10 years or something, or 15 years, that it could increase production by 26-fold in the US alone. So there's a lot of opportunity here to be able to increase the energy production from a renewable resource using enhanced geothermal systems. So for instance, there was, in 2020, there was 5 different topic areas and quite a large amount of funding available for actual research in these areas, from trying to understand how to isolate zones within a wellbore at high temperatures, because remember, we're going in ultra high temperatures in a lot of these areas. So we're thinking of things, greater than 200 degrees C or 250 degrees C. And we have to engineer and mechanically engineer things that can actually go to those conditions. There was another topic on understanding the state of stress in a geothermal field. So that should show you that within 2 years or 3 years, there was 2 different funding announcements with multiple millions of dollars available for research in understanding the state of stress. Also for modeling kind of this combined system, because the EGS is not just a mechanical or a geomechanical problem. It's a multidisciplinary problem, and so having models that can try to understand the thermal, hydrological, mechanical, and the chemical aspects and the effects that are going on within the reservoir is really important. So the development of these models it was a very large topic area. So one of the other ones was trying to design the new well placements at the forge site, because they're drilling new wells to be able to test new technology there. And then finally, understanding the laboratory measurements and then scaling those up to the field measurements as well. So they also just funded, or they're getting ready to, they've just made the announcement to award funding in a really interesting area called innovative methods to control hydraulic properties in EGS systems. And effectively what they're thinking about here for one of the issues is, if you have a fracture system that is very complex and it has different pathways through it from one wellbore to another wellbore, there could be pathways that are wider fractures. So say this big fracture here that connects things could be a wide fracture, and that could be taking up most of the fluid and most of the flow from the injection well to the production well. And if it's taking up most of the flow, what's happening is not enough fluid and water is getting into these other fractures to extract the heat over a wider area. Instead, it's extracting heat from a smaller area. And so to be more efficient, to be able to extract more heat, then we want to be able to say something and do something about these kind of fast moving pathways or fast flow channels that take up the majority of the fluid. And so they awarded quite a few different projects for innovative ideas to chemically precipitate something in these fast moving paths to close them off temporarily, and then widen or create and enhance the other pathways. And then all of the methods that chemically precipitate, or different chemicals that are put into these big fractures to clog them up, they're reversible. So they're working on all of these different awarding teams are working on ways that they can actually plant things into these fractures, clog them long enough to enhance the other fractures, and then have it be reversible. So then you have a very large fracture system with no what's called fast paths, because we want a very wide but efficient at heat extraction system of fractures to be able to put water in on one side and extract as much as we can, or all of it, on the other side. So that gives kind of a little bit of a background of some of the issues and things. I'm not actually working in each of these little areas. I'm working in several of them, but that gives you kind of a broad understanding of EGS and where the current research dollars are, at least right now, are heading. I don't have a crystal ball. I don't know what problems we're going to be looking at in the next year or two, but people are thinking about that now. So this is a good spot to transition into an area that's interesting. It's very interesting for me. It's called non-destructive evaluation. It's ways that we can look at things and understand what their physical properties are, or whether they have damage, without actually destroying them. So the fundamental background of non-destructive evaluation is that it's this examination of an object or something with a technology that does not affect the object's structure or future usefulness. So, we can, if we had in civil engineering a concrete beam, we can understand if the rebar is rusted and it has lots of fractures or if it has fractures inside of it, if we tear it apart and look at it. But then we have a concrete beam that's torn apart. We don't know what to do with it after that. It's just needs to be recycled at that point because it's no longer useful. Or if we need to understand kind of the fractures that are happening within a large dam structure, we can't really chisel it out and look inside of it because it would make things worse for the dam structure and cause large risks. So we need to be able to kind of image these things and look inside of them. And there's a lot of ways to actually do that, which is really interesting. So we're going to talk about several of those. So here's a few of them, and kind of one of my favorite little images of a really good, gives someone a really good understanding of non-destructive evaluation, is a person just holding on to a tree branch, holding on to a tree branch and hearing and listening to the cracking that's going on the tree branch. And they say, oh no, I'm going to fall. That is non-destructive evaluation. You're hearing something that is going on within a structure, and you're making an evaluation of what's going on in order to make your next steps. You're not actually tearing it apart to look at it to see if it's breaking. You can hear it based on the sound that's being emitted. So that's the acoustic emissions part of it. So there's lots and lots and lots of methods of non-destructive evaluation. If medical sensing is radiology, you could do magnetic imaging as well, and ultrasonic testing and optical methods. There's lots and lots of different ways. And you can see someone here with an ultrasonic sensor on a railway be able to see if there's any cracks within the metal beam. You can also see someone using non-destructive methods to try to look inside of this structure on a bridge. Non-destructive methods are also used very, very heavily in environments like at nuclear power plants, because obviously that's an area where it's very, very high risk. And we need to understand if there's any cracking going on within any of these structures. We'll talk about that a lot more in just a second. I think I'm moving a little bit slower than normal. So instead of taking like 5 minutes, we're going to take 2 minutes. And just think about something that's in your life that's both very critical to your day-to-day life, but it's also very, very difficult to know whether it contains any damage. So you don't know if catastrophic failure is coming, but it's possible. So think about that for a second. I don't know if we have a chat window that's for everybody, but you can.
Yep. People can type in the chat if they want to.
Okay, yeah. So, after you think about it for a minute, type in the chat of some of the things that you think are very critical, but are hard to know whether or not they have damage. So that's a good one. Someone says fresh perishable produce that may be spoiled. So that's a good one. So usually we're looking at things in the produce section with our eyes and we're visually inspecting it. But sometimes within the produce, we don't know if something's going on inside of it. So that's when people are picking up the watermelon and they're tapping on it and shaking it and looking at it and looking for these different spots on it. So the tapping on it is a form of non-destructive evaluation. Bike helmet, great example. A car, excellent example. Burning wood for heat. Automotive, and yep, elevator cable, excellent choice. You don't see it ever, but it's very, very important for your day-to-day life. And so that's one of the things that, so we need these kind of non-destructive techniques. Plumbing in an apartment, that's an excellent one. So we need these non-destructive techniques to be able to try to evaluate what's going on. So we can't cut the cable to look at the wires internally. We need to be able to actually understand what's going on. So some of the applications, we already talked about this, is we can apply non-destructive techniques to looking in the subsurface. We can do that for oil and gas extraction. We can do that for geothermal energy. And you could do that in many, many ways. So think of some of the techniques that people use to listen for earthquakes, for earthquake seismology. You can use these geophones to be able to understand some of the small changes that are going on within a fracture system deep within the subsurface. You could use plane-based or satellite-based technologies to look at ground surface deformations, which is really, really interesting. You can see very, very small deformations over time with plane-based or satellite-based techniques. And those are non-destructive techniques to try to image what's going on, sometimes kilometers within the subsurface. So we're going to skim through a little bit of the next couple slides because they're not necessarily geothermal, but at least
can I interrupt there? Looks like Sandy, you've got your hand raised. Did you?
Oh yeah, go ahead, Sandy, please. You are muted. Sandy, you're still muted.
Or if you wanted to type in the chat box, that's.
Yeah, either way, if for something's going wrong with the microphone, please throw it in the chat, either way. Okay, so we'll move on a little bit, but throw it in the chat window please interrupt me. And I may not see the hand, but Scott, thank you very much for pointing that out. So we have these different techniques. They're useful in a lot of areas. We try to see what's going on with the rock material in front of a large tunnel boring machine. It's similar. You don't know what's in front of it. You might need to know how the cutters are wearing as this process is going on. So we need to know how these materials are behaving and what some of the physical properties of these materials are out in front of the cutter, which you can't see into. So we have applications of non-destructive evaluation in tunneling and underground construction, as well as in kind of rock pillar designs for these kind of underground storage facilities. You could imagine that these kind of underground storage facilities are very, very important to be able to predict what's going on with the evolution of these physical properties. What if we have a pillar failure? It could be something that is very, very high risk, and we need to know what's going on within this pillar. So we use these non-destructive techniques for that as well. So we're going to step back to geothermal in just a second before we run out of time. There's also another area that to use non-destructive techniques is a part of the energy industry as well, with trying to understand what to do with hazardous waste. So there's a site in called the Yucca Mountains site that is probably one of the most evaluated sections of ground, definitely within the United States. And it's one of the potential, or at least that was at one point, one of the potential areas to put some of the nuclear waste storage. And so trying to understand the physical properties and the evolution of physical properties as the ground, as we place these things in these underground storage facilities is very important. So non-destructive has a wide implication of both health and safety in many different industries, especially the energy industry. Also with trying to look at being able to go to some of these planetary structures. You may want to be able to, how would you know if you had a shelter on Mars, whether or not you had any kind of fractures developing that are microfractures that may not be problems now, but they could lead to problems later. How do you know that what's going on? We're going to have to implement non-destructive techniques that are continuously monitoring for these things as we start to go out into space and go in and maybe even have a structure on the moon or on Mars, especially with looking at trying to how will these future colonies survive, whether they're in lava tubes or if they actually have these surface structures. Either way, we'll need to understand kind of the evolution of these properties and the damage that's going on. So taking a step back a little bit, we're going to talk, so we have a little bit of NDE techniques. We can measure NDE non-destructively, a lot of different phenomena, both in the lab at small scale, and we can do it in the field with large scale. You see on the left, there's just a Wikipedia image of a geophone. And this is a sensor that's placed in the ground that monitors the displacements over time. And the displacements over time, those are the earthquake seismograms traditionally. So you can monitor the earthquake motions and ground accelerations with this type of equipment. We also can use what's fiber optic sensing to be able to look at different methods of strain within the subsurface or even on a physical structure itself. And you see this is just an image of an area that has some fiber optic cables laid down onto the surface. And we'll talk about fiber optic sensing in just a minute to be able to measure different things at the ground surface. At the laboratory scale, we can do things like CT image even these rock samples, or we can CT image, like you already know about, structures with fractures within your bone. We can also look at pass ultrasonic waves, and we'll talk about that now through the material to be able to understand both the physical properties and whether or not there are flaws in it. So with CT imaging and X-ray imaging, you can see traditionally is radiographic methods are used for looking at inside of our body and looking at bone fractures and things like that. But what we use in geological engineering, we can use these things to look at rock samples to be able to see whether or not there's fractures occurring and where they are within a rock sample. And you can actually map these fractures really well. Or you can see this video on the right, where this is an image of a small volume of a sandstone sample. And you can see all of the individuals, the grains of the material, and the dark areas, the pore space, to be able to understand what's going on inside of the material. And here you can see this is just an open section full of sand of a PMMA acrylic, and it has small fractures within that acrylic. So we can use this CT imaging as a non-destructive tool for these geological engineering concepts. Oh, so somebody said, sorry, I didn't mean to raise the hand. It was a computer issue. Whoops, went too far. So we can also use ultrasonic waves. And you can just quickly look at these images on the top, where there's a sensor here and it pulses a wave through water and it hits this kind of pebble within the water, and the pebble within the water reflects the wave back to the sensor, and it can receive that reflection and be able to say what's going on, where that's located, as well as what it looks like and what its geometric structure is as well. So I don't want to go, I'm actually put too much here. So we also use acoustic emissions, which are the exact same thing as listening for earthquakes, trying to understand how when fractures occur, they generate these elastic waves that are propagated throughout the material. And we can listen for them with geophones, or at the lab scale, we can listen for them with small sensors here. And they're very, very similar to these kind of large-scale earthquake responses. In fact, here a set of acoustic emission waves from a lab test, and here are earthquake seismograms from a Loma Prieta earthquake in California. So they're very, very similar. They're just at much, much different scales. So we could use these in the lab as well to be able to understand how these fractures are occurring in these geothermal rocks. So what I want to touch on last and be able to give everybody at least a few minutes to talk and ask questions. I went put too much here, so we can go through them with questions as well, is kind of what we're working on now in terms of using NDE techniques in geothermal. And so my group does this through the lens of a laboratory experimental group. So we look at using very, very high pressure and temperature equipment. There's a vessel here that we can put a rock sample inside of, and we can make that rock sample experience up to 20,000 PSI in confining pressure and about 1 million pounds in axial force on a cylindrical sample. And while we subject that sample to these heat and stress conditions that it may see in the environment, and subsurface in a geothermal environment, we try to monitor many different geophysical properties and try to understand, one, remember what we said, we needed to understand elastic properties, we needed to be able to understand fractures as well. So elastic properties and inelastic properties, failure and elastic properties. We do this at the lab scale in a high pressure, high temperature environment. And we also try to say something about the damage that's going on within the material. So we have this picture here is kind of a good example, good cartoon image of what's going on. We have some kind of underground structure, whether it's a tunnel or it's some type of geothermal system, and we have a damage type causing event. We need to be able to understand the fractures that are occurring within this. So it's monitoring with non-destructive techniques and then trying to put those fractures in context with a physical model to be able to understand how we're now going to interact as humans with these structures. Because we can't always assume that we're going to have the same physical properties for every structure and every underground environment. These things are changing through time, and we need to understand how they're changing. So at the lab scale, we can create EGS environments in the lab, which is really exciting. So we can do this with very, very large triaxial systems. I say triaxial, it means just stress in 3 directions, where we take large granite blocks or other rock types for blocks, and I say large, it's 30 centimeter cubes for this system. And we can stress these samples that are very large to a specific stress condition. We can drill well bores and have this heated as well, drill well bores, create fracture systems and drill production wells and actually create a real geothermal environment and enhanced geothermal system in the laboratory, which is really exciting because then we can start to study the interactions of the complex system of multiple fractures, elastic properties, stress, and we can do that. And here's a video of some of the small micro cracks that are occurring within this block that's inside of this system, where we have an injection well here that's in black, and it's creating this hydraulic fracture that's going in this direction. So we can monitor as we create these fracture systems as well. And going forward in the future, we're going to be doing this at an even a larger scale. We have some new equipment where we're going to go even larger sample sizes, larger stresses, higher temperatures, and we're going to monitor, excuse me, more geophysical techniques, even fiber optic sensing in the lab to understand strain of this material. To be able to do this, we're going to have large 30 by 30 by 45 centimeter cube blocks, and we're going to create an EGS system with multiple well bores and to be able to test and try to understand what the some of the things that we're looking at are induced seismicity, as well as how the injection in one well bore interacts through the fractures with the other well bores. So I'll probably leave it here to give us 10 minutes. Sorry, that was a little bit rushed at the end. I didn't realize that I put too much in there. But leave it here so we could talk about kind of this future work, or if you have any other questions about any of the other things that we talked about.
Great, thank you. And as folks are thinking of questions, I guess one thing that comes to mind is you mentioned the DOE report, and that geothermal seems poised to really ramp up and scale. I think, given all the challenges that you've identified, what do you think gives the Department of Energy confidence that we're on the cusp of really scaling things up?
So that's probably a question that's above where I am right now. In terms, is probably a good question for the Geothermal Technologies office. But what I think is happening is we're getting enough production from some of the existing geothermal fields within the U.S. and there's enough interest from companies that are actually trying to develop some of these EGS fields that we're at the cusp of being able to really try to actually enhance the ability to produce some of the heat energy. So there are these kind of critical things that we need to look at, but they seem to be relatively well defined. At least the solutions don't necessarily seem well defined yet, but a lot of people are working on very different solutions for them. But there are the problems, at least the near-term problems, seem to be relatively well defined, which is kind of an exciting area. Someone asks, is fiber optic sensor temperature not limiting? So like Sandy, is your question more along the lines of, is there a limit to the fiber optic cable in terms of temperature? Yes, okay. So what's exciting about fiber optic sensing is you can use the same kind of fiber optic cables that you have in your office buildings and things like that. There's these long fibers and they're glass and they have lots of little tiny imperfections in them. And when you shine a light source on one side, all of those little imperfections end up reflecting some of that energy back as well. So you can measure that reflection, and then as the cable is stretched, whether it's stretched because of an increase in temperature making things expand, or it's moved because of an acoustic wave hitting it, or if it's just straining with the rock at a different rate, you can actually measure the response, and it's called a distributed fiber optic sensing. And so you could do that at the ground surface. People do that now for looking at traffic loading on different structures. You can also place the fiber optic cable in a well and do this at downhole. So we do need, for fiber optic sensing, a good understanding of its temperature sensitivity, because it is something that stretches and it actually deforms with temperature. So when we measure these strains from something else, we need to make sure that we understand both the strain of the cable due to temperature as well as in other mechanical type strains. So it does work in some of these downhole environments. There's another question. Someone said, what would be some of the pros and cons of using EGS to replace fossil fuels if it is feasible for large-scale infrastructure? So really quickly, a good pro of EGS is that there's an entire oil and gas industry that has drilling technology, and kind of you wouldn't have to create and ramp up a whole industry of expertise and equipment and know-how to be able to apply some of these same principles, some of these same activities to geothermal. So that's really kind of a great reason to expand geothermal, is because we have so much infrastructure that's already existing, that's used in a similar way in oil and gas. Someone asked, is heat energy capable of being extracted from wells limited over time? How would the well energies go on? Oh, that's a good question. So you can, for instance, if you put water too quickly into a particular area, it could possibly cool down a fracture for a period of time. But that does come back. The heat does come back in that area because it's consistently down there. So what we need to do is actually use data assimilation techniques to be able to design how much fluid we're putting in, at what rate, through a certain fracture system. So that speaks to trying to understand, one, what the fracture system looks like, how it was created, which well bores are open and closed, and pulling water in and extracting water. So it needs to be kind of a system design perspective. Someone said Vox article mentioned 370C temperature above 5 sensing limit. So 370C is pretty high. Yeah, absolutely. There's a lot of geothermal fields. You only need to get steam and boiling water. So a lot of the geothermal fields and a lot of the funding announcements, that's a good point, Sandy. A lot of the geothermal fields and funding announcements are trying to be above 250C. So there's a pretty big difference between 250 and 370. And there's a lot of area to actually work in that area for a lot of equipment. As you go really, really high in temperature, a lot of the downhole tools even stop working. So that's another thing. Mechanical engineers need to be able to understand how to make really good high temperature tools that can go to these really hot environments. So right now we're kind of trying to operate in that 200 to 300 or 350C range, with a lot of the funding announcements specifying try to reach 250. So someone says, any research on heat transfer, optimal heat transfer coefficients of pumped fluid? I don't know of any myself, but I'm positive there are. There's chemical engineers are working in the area of geothermal energy as well. In fact, a lot of the people that were funded recently for the most recent funding announcement were we're looking at chemistries associated with stopping and clogging fractures and making it changing the flow paths. So chemical engineers are actually looking at a lot of areas. It would not surprise me at all if they're looking at different types of fluids. So the one of the issues with that though is lost circulation. So if you lose a fluid that is different than water, then it's kind of expensive. So usually water is going to be what's going to be used most often, I would imagine. What would make a geographical region an ideal site for EGS? So everything moved on me a little bit. So the ideal for EGS, just accessibility to hot, dry rock. So if the hot, dry rock is at a depth of 20 kilometers versus 10 kilometers, then drilling half the distance is going to be a lot easier, a lot more cost effective. So it's just about where these kind of hot, dry rock resources are. And so they're in a lot of areas, and it's just about accessibility, water accessibility, infrastructure accessibility, as well as how to reduce the costs to be able to get the wells and fractures in place. And so a good example is, do we have to drill 20 kilometers or 10 kilometers? The next one somebody asked is, does EGS method result in the exiting of fluid carrying toxic metals? That is an excellent question. And so that is probably slightly out of my area of expertise. So we at geothermal plants need to be able to process the water that comes back up and then gets re-injected. It comes back up and gets re-injected. So anything that is picked up along the way within the subsurface and coming to the surface, we need to be able to process that. And we usually try to do circulation. So it's bring it to the surface, extract heat, process, re-inject. It is a much cleaner method of injection than, say, oil and gas. Oil and gas, you usually inject a lot more different chemicals in it. This is typically a lot less things that are added to the fluids. Because it's a hot, dry rock, it's usually granite. It doesn't necessarily need to have things like what's called clay stabilizers and these other things. So excellent question, Raj. How extensive is oil and gas industry exploration of EGS at this point? So through research or funding, so through research, oil and gas is actually taking a few big steps into EGS as of the last 2-3 years, which is, to me, really exciting. There's quite a bit of kind of internal work at a lot of these companies where they're evaluating where their future is going to be, because they know that at some point they're going to need to transition to some other things, and they're internally evaluating kind of their long-term vision. So and speaking with people from various oil and gas companies as well as service companies, they're looking at it. I don't see yet, probably there is, but I don't see yet oil and gas companies making funding available to outsiders like universities and things like that for those areas. But maybe that's happening at the small scale. I don't know. But they are looking at it now more than they have been before. There's actually conference presentations from oil and gas companies that are all about geothermal, which is kind of exciting. There's another question. So someone says, nope, that's not a question. That's just Scott saying, here's some links to maps regarding different geothermal technologies. Thanks.
And there was a question before that. Do you look at corrosion issues?
Oh yeah, corrosion. So that's a big issue in a lot of areas, actually. So some plants, you have quite a lot of scaling inside of the pipe. So what happens is you end up with, you have a pipe that this diameter, and as you're flowing through it, you're precipitating things that's inside the water, and it's precipitating onto the pipe, and then it's closing your diameter. So a lot of geothermal plants, even the traditional geothermal plants, have to go through shutdowns every once in a while to actually clean off the scale that's occurring within their pipes, within their plant. And so that's actually kind of a big issue. That's a big opportunity for chemical engineers as well as chemists to be able to look at how to effectively not have scaling be an issue from these types of water inside of a geothermal plant. So that's also a really cool area of current research. Not particularly my area, but it is very interesting.
All right, well, I think we're about out of time here, but thank you so much, Professor Hampton, for your presentation, and thank you all for your questions. Great discussion here, and we'll look forward to seeing many of you in a couple of weeks when we have Professor George Huber, who will be talking about different bioenergy technologies. So thanks, everyone, and hope to see you in a couple of weeks.
Yeah, thanks for the questions.